Okay, my name is Eli Kavan, and I go to the University of Waterloo, and I'm going to be doing some instructional videos based on some of the courses that I'm taking. So this is my first one. Let's start on something pretty easy. We're going to start with second-order differential equations. So, second-order differential equation is just an equation that you have second-order derivative in it, so a second derivative. So, our simplest one is y double prime equals y. So, assuming that you have some background into differential equations, or else I don't think you would look at second-order differential equations until you look at first-order differential equations. So let's think about this equation. What's a function that we can take its derivative of, and then take the derivative of its derivative, and still get that function back? And if you think about it for a bit, y equals e to the x is an obvious function that we could choose. So we're going to use e to the x a lot in second-order differential equations because it's its own derivative. So again, assuming that you've done first-order differential equations, we're going to use the same kind of theorems and principles and properties when we're solving second-order differential equations. So mainly, the most important one is principle of superposition. So principle of superposition, if you haven't remembered, is that if you have two solutions, y1 and y2, then the sum of the solutions to a differential equation, so for example, y1 plus y2 is also a solution, right? So y1 plus y2 equals another y. That's a different solution to that differential equation. So when we solve second-order differential equations, the first thing we look for is to use the method of undetermined coefficients. That's the easiest method. The other method I've learned is Laplace transformations. That's obviously a little bit harder, and I'll do a video on that. So what's the method of undetermined coefficients? You've probably seen it in first-order differential equations. So what we have is we have a general solution, y general, and that's made up of two parts, homogeneous solution and a particular solution. So that's YH and YP. So what's YH? YH is the solution to the homogeneous equation. So for example, and by homogeneous, I think I should make that clear. Basically, you have your equation equal to 0. So all you have are derivatives of your function, and you have no other kind of a forcing function, what we call it. So let's say you had y prime. Let's go back to first-order differential equations. If you had y prime plus y equals cos t. Cos t is your forcing function because it doesn't contain your variable of interest or derivatives of your variable of interest. So if we were to do method of undetermined coefficients, what we would first do is set y prime plus y equals 0, and we would solve that, and that's easy. And then what we do is we look at our table. There's a table. It shows you, what kind of solutions you should pick if you have cos t. Okay, so what do I mean by, you have particular solutions that you pick? Well, basically what we have is for forcing functions, we have a table of yp's to sub in, and we sub this yp into our original differential equation with the forcing function, so not the homogeneous kind. So let's say we had y prime plus y equals cos t. We would find our yp using a table. Our table would tell us, if you have cos t, for example. So for cos t, the table says use a cos t plus b sine t. Okay? So we would sub this into our original differential equation with the cos t at the end, and then we would solve for a and b just by looking at the forcing function and seeing what we need. For example, so if we sub this actually into this equation, right? Well, I usually do this on the side. So yp equals a cos t plus b sine t, and yp prime equals, what's the derivative of cos? It's negative sine, so we have negative a sine t plus b cos t. Hopefully this works out. I just made this up now. So now let's put this into this equation, right? And just collect like terms. You can do this all at once. So yp prime plus yp will equal what? Let's collect, let's say negative a plus b sine t. Just collecting like terms. And we're going to add a plus b cos t. Now, using this equation, I can figure out the values of a and b that I need so that I get just cos t, right? I just want cos t. So, what does that mean? It means I want b minus a to equal 0, right? Because that's in front of sine. I don't have sine in my forcing function. And I want a plus b to equal 1. So, simple algebra, right? We have a equals b. So if we sub in here, we have 2a equals 1 and a equals a half. And if a equals a half, b equals a half. This is, and for this kind of thing, you might not need to number your equations, but if you're ever having trouble, one thing I would look for is numbering your equations, especially if this, if it gets really complicating, if your forcing function is very complicated. So now we have our whole solution. So right, so y general equals y homogeneous plus y particular. Our y particular then is 1/2 cos t plus 1/2 sine t. I never actually found yh because I'm stupid. But so for yh we had y prime plus y equals 0. So that means y prime equals negative y. So you can solve this. You can solve this homogeneous equation in in a variety of ways. You could use, all the methods you've learned for first order differential equations. You could maybe it's separable. Maybe you want to use your linear formula with the integrating factor, or you could just do this by inspection. When I look at this, so I have a function and I take its derivative and I get a negative. So I'm thinking e to the negative t, right? So let's check. What's the derivative of e to the negative t? It's negative e to the negative t. So y prime equals negative y, and we have our solution. So our solution is y general is c1 times e to the negative t plus 1/2 cos t plus 1/2 sine t. Okay? So and if we had if this was an initial value problem and I had y prime equals this or whatever, then I could solve this. I could solve the c1 and get a solution. Right now this is just a family of solutions based on c1, which is the constant, obviously. So how does this all relate to second order differential equations? Well, in a very simple way. So the difference between first order and second order differential equations is because second order differential equations are more complicated. Basically, to find the homogeneous solution, we're always going to sub in e to the mt or e to the mx, whatever variable you prefer. So and what we'll get is we'll get a characteristic equation, which is what we call it. So let's take an example. Let's say I have y double prime plus 2y prime plus 3y, and if we're finding the homogeneous equation, this has to be 0. So I'm going to sub in e to the mt. So take two derivatives of e to the mt, you're still going to get e to the mt plus 2 e to the mt plus 3 e to the mt equals 0. Now we're gonna oh, I made a terrible mistake. And the mistake that I've made, if you've caught it, is that the second derivative of e to the mt is m squared e to the mt, and it's 2m e to the mt plus 3 e to the mt. That's, that's unfortunate. So that's what happens when you rush. So we're going to factor out e to the mt, and we're going to get m squared plus 2m plus 3, and that equals 0. So this is the characteristic equation I was talking about. So what we notice is that e to the mt will never equal 0. So what I'm going to do is just divide out e to the mt. It's pretty much useless to me. So I'm gonna get m squared plus 2m plus 3. Okay? And that has to equal 0. And now this is just, this is a, I don't know, grade 8 problem. So find the roots to that quadratic equation. Now you can use negative b plus or minus square root of, whatever, quadratic formula, or you can factor in your head or whatever, but you get the roots to this equation, right? And then finding the particular solution is the exact same as if it was a first order differential equation. So what you're going to get is just the only difference between a first order differential equation really and a second order differential equation is that you'll get two constants. So assuming you have two roots to the characteristic equation, and we'll talk about one root, two root, because this is where the complicated part of second order differential equations come. How many roots do I have to this quadratic equation? Do I have one root, two roots, or no roots? Complex roots. There's never no roots. Complex roots. But yeah, so we'll, if assuming we have two distinct roots, like in this case, well, our solution will look like this. Y general will equal our y particular. That's whatever our forcing function is, and assuming you've done the method of constant coefficients with first order differential equations, you know how to find that. And then we'll have plus c1 e to the m1t, where m1 is our first root to that characteristic equation, and then c2 times e to the m2t, and that's our second root. So the three cases we would have with this characteristic equation is either you have two distinct roots, right? Two distinct. Or we have a double root. Double root, if you recall, looks something like this. If we had a graph, it touches at one point, right? So we're going to have one root instead of two. It's, pretty simple. And complex roots. All right. So I think we'll tackle, we've done the distinct roots. I think we'll tackle complex roots first, because they're actually very simple. If you haven't seen complex numbers, then it might be challenging. But basically, you're gonna have your quadratic equation, negative b plus or minus root of b squared minus 4ac over 2a. And so if this this argument inside of the root function is negative, you'll get complex roots. And all you're really gonna do is just basically don't overthink it. When I do it, I just do this. Imagine taking the negative outside the root and replacing it with I. So let's say I had the root of negative 4. All that is, it's I times the root of 4, and that's 2, so it equals 2i. Okay, so it's simple, and so you might want to look at some videos of solving or working with complex numbers if you have trouble with that. So you'll get something along the lines of negative b plus or minus something ai, let's say, right? And this is over 2a, obviously, but we'll just imagine that that's our answer. Our answer comes out to be negative b plus ai. So obviously your two roots then are negative b plus ai and negative b minus ai. But there's a little bit more of a trick with that. And basically, I'll sum up the trick like this. We're going to end up using cos and sine because we know from Euler's formula, e to the it equals cos t plus I sine t. right? Sorry, yeah. What we'll end up having is the homogeneous solution actually ends up being e to the negative bt, right? That's just this number, times cos of ai, cos of a t is what I meant, cos of at plus sine of at. And obviously there's a proof behind that, or whatever, but I'm not going to show that here. And in practicality, when you're working with differential equations, you don't need to see the proof to know what you have to do. So obviously, if this b is 0, if you have a b value of 0, you're not going to have e to the bt. You'll just have cos at plus sine at. Okay? And so then our next, our final thing to tackle is the double root. That's if you have only one root to this characteristic equation. And then you will need to use variation of parameters, which I'm sure you will probably have seen if you've done first order differential equations with constant coefficients. But to sum it up, that's more complicated to talk about, but really all you're going to be doing is you'll have your homogeneous solution will be t times e to the mt plus e to the mt, right? And I'm only using mt instead of using, when I used two distinct roots, I had m1 and m2. Now I just am using mt because there's only one root. So that's a variation of parameters in simplified terms. So I hope that helped. And now you'll be able to solve basically any nice second order differential equation that they give you. And please leave some comments. Tell me, what I can do better. Obviously, it's my first time doing this, and I'm excited to do this. I like teaching, and hopefully you can learn something and you can teach me something too. Maybe if I make a mistake. So thanks for watching, and bye.